Okay, so we're in the last, the last main topic in statics is friction. There's sort of three subsections to that. We talked about square-threaded screws. That's the one that basically reduces to calculations of a block sliding up or down an incline. And then we have to talk about bearings, and there's two kinds of bearings. We'll do that today. And then the last one is belt friction. Anybody have any homework questions or anything like that before we get into the new stuff? Okay. So we're talking about friction. And we're breaking that up into, hold on. Okay, so friction. We're breaking that up into square-threaded screws. And bearings. And there are two types of bearings we'll talk about. The first one is called journal bearings. And the second one is thrust bearings. And then the last thing we'll talk about is belt friction. We've done this, so now we're moving on to bearings. And the first one is journal bearings. So I'll draw a picture of what this is. You can think of this as like a bearing that wheels are rotating, that's facilitating wheels rolling. So this would be like you have an axle and it's supported by a bearing like this. And this is turning. And there is a force being, like a weight being applied to this axle. We can imagine that it's a total weight of W, but we can split it up so it's symmetrical. Okay, so that's a journal bearing. And it would be, similar to if this thing's upside down, you can imagine that that weight is actually being applied by the ground force acting on the wheels. And then the second one is a thrust bearing. And that's one where you have this thing rotating. And it's in contact with a surface like that. And the weight that's pushing these two things together would be like this. Those could, both of these two can happen at the same time if you think of like a, if you think of an axle with a flange, that's being put in something like that, you know what I mean? So that flange would apply thrust friction on the wall. There is what it looks like, a wall, and the axle would have journal bearing friction. Okay, so this would be a case where you have both of those two together. I don't know if I talked about the type of friction that we're talking about here. When you did in Physics 1, sliding of blocks up and down inclines, do you remember what type of friction you were talking about? Like what's the nature of the surface between those things? Do you remember that? Like, did you talk about what type of oil it is or whatever? It's dry friction, okay? So the reason for that is the whole idea of the friction force being proportional to the normal force pushing the surfaces together, that only applies to dry friction. So if you have this thing bathed in oil or whatever, then that's viscous friction and you have to use sort of a different approach. In some cases, you may be able to approximate that, but so really think of the calculations that we're doing as applicable mainly to, I mean, you could use like some kind of like graphite, you know, not a lubricant, but like a something to reduce the friction. But remember that all these derivations are for dry friction. Okay. All right, so let's start with journal bearing friction. And I'm going to do a free body diagram of the axle, like from the side. And I'm going to do it blown way up because we're going to have some small angles and stuff. So you have so look at this picture that I drew here. If we're doing a free body diagram of the axle, we have a total weight of W on this thing, one on each side, right? But we're just looking down the pipe, so you have both of those. And so this is going to be W. And if, so this thing is, we're assuming that it's spinning this way. Okay, so that's the direction of motion. That's not a couple or anything. That's the direction of motion.
Do we always orient it clockwise?
Yeah, you might as well. Yeah. Because really this is just kind of a way to tell yourself how to do this calculation, you know? And you can think of any, so in the case where it's upside down and this is supporting a vehicle or whatever, just think of it this way always, and it'll let you do the calculations. Okay. Okay, well, what the effect of friction is that the contact force from the bearing itself is not going to act along that center line. It's going to act over here. Okay. This is in static equilibrium. And so the key thing is, so basically like what we're looking for is what's the couple M we need to apply to maintain a constant angular velocity. You know, just a constant roll. Let's just call it rate of rotation. Well, the couple that we're going to need to apply is going to be that weight W times this distance that I'm going to call rho. Okay, so really what we're trying to do is calculate that distance rho. I mean, that's really our whole job here. Okay, how much has that force applied by the bearing become offset from that center line? Okay, so how are we going to do that? Well, let me move this W over because stuff's going to go in that space. Well, we're going to break this up into, you know, this force W, we're going to break it up into two pieces. One is the normal force. And one is the friction force. And this makes a right triangle. And so the magnitude of this friction force is the coefficient of friction times the normal. How does that help us? Well, the angle, this angle here for this triangle is the same as this angle. I'll call that theta. Okay. So given that we know the legs of this right triangle, we can figure out that angle theta. And that angle theta, now since we know that this is the radius of the whole axle, we can use that to figure out that rho vector. Okay? So if you can find that theta for the right triangle, then you can use that to find rho. And rho is the whole deal, you know? You know, this is the what we need to calculate. Okay, so once you figure out that relationship, then it's kind of just SAT math questions to figure out what that rho vector is and come up with the couple. Are you with me on that? So how do we come up with that angle theta? Well, the sine of theta is equal to the coefficient of friction times n. That's not right. I failed the SATs. Okay, tangent. Tangent of theta is mu times n over n. You can see the ends cancel out. And so the tangent of that angle is just equal to the coefficient of friction.
So the normal force doesn't even matter for that.
That's right. Right.
Can you explain why the W gets offset?
That's a good question. It's an experimental thing that that you can see if you do the experiment. If you just calculate the center of pressure, like if you integrate all of the forces being applied by that axle, being applied to the axle by the bearing, you'll get a distribution of forces. If you integrate them and figure out where where you can treat it as an equipolant system, you'll see that it moves forward like this.
This is because it's spinning.
Yes.
So if it's spinning the other direction, presumably
It would go to the other side. That's right. Yeah. I mean, I guess, like, you can think of what would happen if there was a perfect friction contact. If it wasn't allowed to spin, if you started this thing rolling, it would roll up it would start rolling up the incline, and that's kind of the effect of what's happening. You follow me on that?
Okay, kind of.
Kind of, yeah. I mean, like if this was a ramp and the friction was enough that there was no slipping at all, if you started it rolling this way, it would roll up the ramp. And that's kind of what it's doing, trying to roll up the bearing.
Okay.
Okay. So tangent of theta is this. So theta is equal to inverse tangent of the coefficient. And now we want to calculate rho. Rho over the radius of the axle is sine of theta, which is equal to the sine of the inverse tangent of the coefficient. And so rho is equal to r times the sine of the inverse tangent of mu. Well, more SAT type math, if you think of a right triangle where the tangent is mu, so you can think of this as mu, and this is 1, and this is theta. Then from the Pythagorean theorem, this is equal to 1 plus mu squared square root. Okay, and so the sine of that angle then, this rho is equal to r times mu over the square root of 1 plus mu squared. And so since the couple is just the weight times this row vector, then the couple is equal to the weight times the radius of the axle times mu over the square root of 1 plus mu squared. Okay, well, this is a formula that I could just give you, but I want you to remember how this works, because to be honest, I don't really see I don't see a ton of usefulness in this dry friction calculation. I think it's really the way that you're putting ideas together that's useful here, you know? And so, this is the formula. But just like for the square threaded screws, I want you to know this derivation. It's not too hard, you know. I want you to go through the derivation. Okay, so anybody have any questions first about like the trigonometry or anything, or did I go through anything too fast? I remember doing stuff like this in like pre-calculus or something, the sine of the angle that's the tangent of whatever, and you set up, remember doing that? Well, you don't even have to do that for me. Because if you're doing this calculation, like, okay, you have a number for this, okay? Go through, calculate a number for this. It's going to be some very small number of degrees, you know, 0.8 degrees or something. And then you can just take the sine of that number of degrees. And so all this is kind of cute stuff that mathematicians like, but you don't need to do that to show me that you're following what I'm talking about, okay? So let me do let me just do an example. Okay, so let's say that there is a pair of wheels and you have bearings like this. And for symmetry, you have 2 of everything. And so let's say that the ground is pushing up on each of these with 1,000 newtons of force. Well, let me describe it better than that. Let's say the weight of the vehicle is applying a force of 2,000 newtons. And let's say that the coefficient of friction, we're talking about kinetic friction because we're assuming that this is rolling and we want it to keep rolling at a constant speed, is 0.05. And what's the couple required to keep the vehicle moving with a constant speed? Okay, well, we're going to do this for one of these 2 bearings. So one bearing deals with half of that weight. And so a free body diagram of half of the axle. Looks like this. And like you said, I'm not even trying to wrap my head around what directions things are going or anything. I'm just going to keep drawing the same picture. So there's the center line. We have a weight acting down of, the whole thing is 2,000 newtons, so this is going to be 1,000 newtons. To be in equilibrium, we also have to have a force here of 1,000. And that's made up of a normal force. So that's perpendicular to the axle at the point of contact, plus a friction force that's perpendicular to that normal force. So these two are perpendicular. This one is the normal force. The green one is the friction force, so that's 0.05 times the normal. The angle that we want is both of these two thetas. Okay. What we're trying to get to eventually is this distance rho here. So the tangent of theta is equal to opposite over adjacent. So 0.05. Everyone with me on that? And so that angle theta is the inverse tangent of 0.05. You can keep this in degrees, that's fine. And so, I mean, whatever your calculator's in is fine. Okay, so one other thing that I need to give you here that I didn't is you're going to need to know the radius of the axle. So this would have to be given. Radius of the axle, let's say that it's 1 centimeter. Okay, so can somebody have a calculator that'll calculate this inverse tangent? What do you get for that angle theta? 2.86 degrees. Yep. And so now the hypotenuse of the triangle on the axle is the radius. And so rho over 0.01 is the sine of 2.86 degrees. And so rho is equal to 0.01 sine of 2.86 degrees. And what do you get for that?
4.99.
4.99 times 10 to the minus fourth. And that's in meters. That's that rho vector. Well, what we're really trying to figure out is the couple that's applied. So this 1,000 Newton force pushing up is applying a couple that's trying to slow this rotation down. Okay, so in order to keep this moving with a constant speed, we're going to have to apply an external couple that's equal and opposite to this. And so the couple we'll have to apply is 1,000 times 4.99 times 10 to the minus fourth. And so that is 0.499 Newton meters. So that is the couple, the reaction force applies to slow the rotation. So to maintain a constant rotation, that's also the required couple from the motor or whatever.
Then we multiply by 2.
Yeah, so it depends if you want it for a single axle or the whole thing or whatever.
So,
I know if you're making like a simple little like robotic vehicle, you probably have a motor in each axle, so each one has to apply that.
so the more efficient it is, the less, lower row will be more small.
Yes, exactly. Yep. The more efficient it is, the smaller that angle will be and the smaller row will be.
Can you get a row vector larger than the radius of the circle?
That's a good question. And what I mean by that is that I don't have a very good answer for that. You can get, so what that would take is a coefficient of friction bigger than 1, which you can get actually, like the coefficient of friction between like rubber and concrete is bigger than 1 in a lot of cases. I suppose that means, yeah, I'd have to think about that more. In practical cases, that would never happen. I mean, if you're building this thing to roll, then you would never build it with concrete on one side and rubber on the other side. You know, you try to reduce that coefficient of friction, but man, I think I'd have to think for a while to figure out whether, like, what would happen in that case.
I had a question.
Yeah.
I missed that part of the lecture, but how do we reason that the 1,000 newtons is like in front of it?
Yeah. So, Fred asked that too, and I think I gave him an answer that he wasn't in love with, but I'm going to tell you the same
Maybe
thing
I'll
and
like it.
see how you feel. Yeah, maybe you'll like it better. But if you imagine, so we're talking about friction, right? So what does this friction do? If you imagine enough friction that you have rolling without slipping, okay? So right now we have friction that just slows down the spinning, but if you have enough friction that it just rolls, and imagine that it's not in a bearing, a circular bearing, but it's just on a ramp. The effect of that friction is that it will roll up the ramp.
Yeah.
Okay.
That makes sense.
Inside that bearing, it kind of does the same thing. If it's spinning this way, the center of pressure from the bearing to this moves to this side. That's an experimental fact that you can measure the center of pressure and you can see that happens. But I think the easiest way to think of it is to think like, oh yeah, it rolls up here a little bit, because of the friction. I think that's a accurate way to think about why it happens. Yeah, in your head, if it makes sense in your head, that's good enough, because you're just trying to remember how to do this stuff, But, so the real answer is put a pressure sensing material on the bearing, calculate the distribution of pressures as you go along, integrate those to find the total force, find the center of pressure where that total force is equivalent to the distributed pressures, and you'll find that center of pressure moves up that way. It's an experimental fact,
So, well, the faster you're spinning, the more resistance there is, correct?
Okay, that's the other thing here. We are talking about dry friction, which is arguably not the most useful kind of friction to deal with if you're talking about rolling wheels, rotating axles, because you're going to use viscous friction for that. You're going to use oil, With oil, you're right. With viscous friction, the faster it's spinning, the more the friction, the bigger the friction is. But with dry friction, that's not the case. If it's moving at all, then this is the friction.
That's it.
0.05 times the normal, and that's the end of it. Yep.
Does the vector move kind of like, say you're inside the wheel and you're like walking along inside, you'd be moving up the wheel, or is that not?
Where does this move?
Yeah, so like say you're inside like a hamster in a wheel.
Yeah.
If it was moving the wheel, it would be moving along the wheel to propel it forward. Or is that not anywhere near?
Well, okay, so this is an axle, not a wheel, but you could think of it, I guess, that way. That's fine. And then, so to propel it, you would be applying a downward, yes. Basically, to propel a wheel like this, if you didn't think about the friction, you would apply a downward, your weight force, up on this side of it.
Yeah.
And that would produce a moment in the same way this produces an equal and opposite moment.
Okay.
So what this is doing is the exact opposite of what a hamster does to make it rotate, yeah.
So you could have any weight as long as it's this side of the center of pressure and it wouldn't spin the wheel.
Okay, say that again. You could have any weight.
Like I'm imagining the hamster being
Yeah.
on the right side,
Uh-huh.
but not past the row vector. And in that case, it would not spin the wheel.
If the hamster's wheel had friction, you mean?
Yeah, just
Yeah, then we'd be talking about, so right now we're talking about kinetic friction. So we're assuming it's spinning and we just want to know to keep it spinning. But remember, if this was static friction, it's sort of the calculation would look similar, but you'd have the static coefficient of friction, which is a little higher than the kinetic coefficient of friction. And then at that point, you'd be calculating the maximum friction force that this can produce before motion starts. And so yes, in that case, which is a little different than since we're thinking of it spinning, but in that case, the thing would be at rest. And if the hamster applied, well, what really matters would be the hamster's row times its weight. But if the hamster's row times its weight didn't exceed that threshold, then the thing would stay static. Yep. Just like if you, like I can apply a small force to this and it doesn't move because the force I'm applying doesn't reach the threshold that the static friction can apply. Yeah.
We were considering the mass of the journal bearings. How would that affect our calculations?
Just lump that in with the weight of the vehicle. You know what I mean? So yeah, those just go right into the weight. So that's not anything like kind of new that you have to think about. You just throw it in there. Any other questions about that? Okay. So now the one with more steps is thrust bearings.
Just gonna drop it.
So this is a case where you have, and we're assuming this is a circular object, by the way, just because the integration we're going to have to do would be a pain if it was a different shape, but you'd still do it kind of the same way. But let's say that it's rotating like this, okay? And the thing resisting rotation this time is the contact between the end of the this cylinder and the ground, okay? Like think about here, like where is the contact that's causing the friction? In a journal bearing, the contact that's causing the friction is this. Are you with me on that? So that red is where the contact is happening. In this case, the contact that's causing this couple to be applied that we're going to have to overcome is that. Okay. In the case of the two together, you know, I drew that picture of a case where you could have both together. There would be a surface like that. And then there would also be a surface like this. And you would have to do both of those and just add the two couples together. Okay, and we'll call this N. This one you could have either case. You could have, I mean, really in both of them, you could have either the static case or the kinetic case. This one, it's more likely that you would have the static case and you're trying to figure out what's the maximum couple you could apply before it started to move. Okay. All right, so what we're going to do is imagine the red shaded contact region. And imagine an infinitesimal ring like this. I'll do that green. So this green shaded region has an area of, so what's the area of that? This is a trick that you use all the time in integration problems involving circular shapes. Imagine just stretching that thing out into a rectangle. The thickness of it is what we're going to call dr, okay? The distance from the center out to it, we're going to call lowercase r. The radius of the whole thing, we're going to call capital R. Okay, so this is like a constant we're going to use. So the green shaded region has an area dA, it's infinitesimal. And it's equal to, if you stretch that out into a long, thin rectangle, that rectangle has a thickness, I'm going to draw that here. The thickness is dr. What's the length of that rectangle? It's the circumference of the circle. So that's 2 pi r. Okay, and so the area of this thing is 2 pi r dr. And so now let me just explain kind of where we're trying to get with this. So we are trying to figure out for each one of these infinitesimal rings what the infinitesimal couple is that its friction applies. Okay, so with this ring, it's more complicated than the journal bearing case, because depending on how far this infinitesimal ring is from the center, even if the normal force were the same in this ring as one closer to the center, it has a bigger moment arm, and so it's going to apply a bigger couple. Okay, and so what we're going to do is figure out the infinitesimal normal force on this ring. Then we're going to multiply that by the friction force we're going to multiply that, the normal force, we're going to multiply that by the coefficient of friction to get the total friction force applied by this ring. And then based on the moment arm of this ring, we're going to multiply it by the moment arm to get the couple of that ring. Then finally, we'll integrate them all. Okay, so it's kind of like a pane, but each one of these rings applies a different couple per normal force based on how far it is from the center, okay? Even a big normal force applied right at the center doesn't provide a couple, okay? Even a small normal force at the outer edge will provide a relatively big couple. Okay, so that's what we're gonna do. And let me just outline that, and then we'll do it next time. So here's what you're gonna do. First, you're going to find the normal force dN for, an arbitrary green shaded ring. Then you're going to find the infinitesimal friction force for that green shaded ring by multiplying the coefficient times what you just found. Again, this is still for the green shaded ring. Then you're going to find the infinitesimal couple. As the moment arm R times this infinitesimal friction force. And then finally, you're going to integrate it. So the couple is the integral of dm. If you just remember those steps and don't remember, like, I would say don't try to store how you do each one of these steps. You can figure that out when you get to it. Just remember the steps you're going to follow, and it won't be too hard. Okay, but we'll go through it on Wednesday.
Cool.
Okay, that's all.